Okay, so now we are going to talk about the architecture of ARM M4, and gradually we will discuss how to access the microcontroller, program the microcontroller, and so on. Okay, let me check if the recording. Okay, the recording has been started. So in the last class we were discussing about the ARM architecture, and some of the important points of the ARM architecture are listed here. We are basically talking about ARM Cortex M4. Okay, it is a 32-bit processor. Remember, here in this processor both data and address lines are of 32-bit. Okay, so remember this thing. It is not like 8085. In 8085, there were two different size of the address and data bus. For example, the data bus was of 8-bit, right? And the address bus was of 16-bit. Okay, so address bus decides the size of the memory which the microprocessor can access,
Excuse me,
right?
sir.
Right, yes, yes,
Excuse
what
me, sir.
happened?
Your screen is not visible.
Yes, sir.
No, you are not presenting.
Okay, just let me check. So I have not started the presentation. Okay, now is it share? Okay,
Yes,
can
sir.
you see the screen now?
Yes, sir.
Okay, so in 8085 there were two different size of the buses. Data bus was of 8-bit, okay, and address bus was of 16-bit. So address bus will decide the size of memory which you can handle, and data bus will decide the size of the data which is to be processed. Okay, so in case of ARM Cortex M4, it is a 32-bit processor. Both data and address bus are of 32-bit. Remember this. Okay, so 32-bit means, can you calculate what is the maximum size of memory which the ARM Cortex M4 can handle? Maximum, yeah, that's okay, but what is the size of memory in terms of bits, bytes, kilobytes, megabytes, and so on? Can you calculate what is the size of this memory, 2 to the power 32? Remember, when I'm giving a lecture, na, keep few things open around you. For example, here you can see I have a calculator. Okay, so keep these things around you so that whenever I ask something, na, you please try to solve those questions so that you can answer it quickly. Okay, at the same time you can practice it when I'm giving the lecture. Okay, so 2 to the power 32 is 4 gigabyte. Okay, 4 GB. So maximum size of memory which ARM Cortex M4 can handle is 4 GB because it has got 32-bit address line. So 2 to the power 32, 4 GB of memory it can handle. Now, it is built with a 3-stage pipelined hardware architecture. So we are just going through the things which we have already studied. Hardware architecture, I told you in the last class also. In hardware architecture, the data memory and the code memory, okay, are two different memory areas. Whereas in case of Newman, okay, Newman, I think this is the spelling. Okay, von Neumann architecture. Both data and code reside in the same memory. Data and code reside in the same memory. If you can recall 8085, we used to keep both the data and the code in the same memory itself. We were not having two separate memories to keep data and code. Okay, so this is the hardware architecture. So ARM Cortex M4 follows hardware architecture. What is 3-stage pipeline? I will come to that in the coming slides. Okay, so this is new term for you. I will discuss it in detail. Okay, it has got single precision floating point computation unit. So remember, of course, I told you that the latest or the upcoming microcontrollers have a separate unit for floating points. Okay, so to handle floating points. So to handle floating points, these microcontrollers have a separate floating point unit in the microcontroller itself. So remember, ARM Cortex M4 follows single precision floating point system. Okay, so floating point unit can be of two types. One is single, okay, precision, and the second one is double precision. Okay, so there are two types of precision. So remember this thing. I will cover this part also in detail in the coming lecture. So these are new topics for you. Okay, single precision unit, double precision unit. Okay, now it has got a MAC unit, which is multiply and accumulate. So in single cycle itself, it can do the multiplication and store the result in the accumulator itself. In the single cycle, when I'm saying single cycle, it is the clock cycle. Okay. Okay. And it is closely, or it is very tightly integrated. Tightly integrated means the components are very close to each other. What does that mean? The ALU, the memory, other peripherals, they are very close to each other. They are not kept far apart. So what is the advantage of that? It reduces the system area. Of course, the chip's area is reduced. At the same time, it improves the latency of the interrupts. Latency means the time taken for the interrupt. So now, for example, if the ALU is here, assume, okay, ALU is here. You have memory which is close to it, memory, okay, and then you have NVIC. I will come to this also. Okay, vector network, not vector network. Okay, the vector interrupt control. Okay, so if they are close to each other, that means the interrupts will be listened or will be served in a very short time period. So the latency, the delay to listen to an interrupt is very small because of the tight integration of the all components within the M4. Okay, we will look into the architecture in the image also. That will clear many of the things. Okay, this Cortex M4 processor can implement both 32-bit instructions as well as 16-bit instructions. So it supports both. Okay, so it is not that because it has got 32-bit processor, it will only support 32-bit instructions. No, it also supports the 16-bit instructions which were used in the which were used previously in any other ARM microcontroller. So it supports both 32 and 16-bit instructions. We call them thumb 2 instruction set. Okay, so the instruction set the ARM Cortex M4 uses is thumb 2 instruction set. Okay, which includes both 16-bit thumb instructions and 32-bit ARM instruction. Remember, this is very important that ARM instructions, when we say ARM instructions, they are 32-bit instructions basically. Okay, but when we say thumb instructions, because these are the things which will come to you again and again, thumb instructions are 16-bit instructions. Okay, and it supports both 16-bit as well as 32-bit instructions. Okay, the processor can be switched to ultra low power mode. We will come to this also, what ultra low power mode is, and it can be pushed into deep sleep mode. Okay, it is not only supporting sleep mode, but it also supports deep sleep mode. What does that mean? That when I push the system to sleep mode, when I push the system to deep sleep mode, how much power I can save? That's one very important parameter. So because nowadays you can see the sensors which are used in IoTs or the boards which are used in IoT applications, they require very less power, almost zero power. Okay, so most of them are nowadays using microwatts. So to have that kind of facility, you can push into deep sleep mode. For example, when your computer is not working, automatically it goes to hibernating mode. The monitor gets off, the computer goes to sleep mode, so that it can save power. If you are not using your computer for more than 5 minutes or 10 minutes, it goes to sleep mode. And similarly, you can program your system using these kind of microcontrollers, so that you can push these microcontrollers into deep sleep mode. Not only sleep mode, deep sleep mode, which further reduces the power consumption. Okay. Okay, how many of you know that your computer can go to hibernating mode? For example, I can just show you. Okay, so control system, power and sleep settings. This is the operating system's feature. Okay, you can see here, screen goes off when the power turns off after 10 minutes. That means if you are not using your system for 10 minutes, it will go to the screen will go to sleep mode, or it will get disconnected, or it will get off. Okay, similarly, when the PC goes sleep mode, I can push this after 25 minutes, 40 minutes, or 4 hours, or whatever time. If the power is connected, even after that, if the computer is not being used, I can push it into sleep mode after 25 minutes. Okay, or I can push it to never. Now my system is not sleeping if the power is connected. Okay, I can change this setting. So this way I can save some power which my system can consume when I am not using it. Okay, so these are the things which you can keep in mind. These are the general features. Now let us talk about the modes and the states, or the levels in which the ARM Cortex can work. What are the different modes, different states, and so. So we are talking about ARM Cortex M4. It has got privileged levels, or levels we can say, modes, and states. Okay, so we can classify them in three different ways. I will show you in more detail in the next slide. But before that, what does that mean, privileged levels? So, okay, so there are two different types of privileged levels. One is privileged level and unprivileged level. There are two modes in which the ARM Cortex M4 can work. One is thread mode, other one is handler mode. There are two states in which the system can work. One is called thumb state, and the other one is called debug state. So these are the six classifications of levels, modes, and states. What does that mean? For example, let us talk about the privilege level. So when we are using any software, for example IAR or any other software, Keel or any other software, all the instructions can access the privilege level mode, privilege levels in the microcontroller. Unprivileged levels are those levels in which software has limited access to some of the registers, like priority masking register. We cannot go and directly change the priority masking registers with softwares directly. You can go and of course change the register itself. There is a different way to approach that, but otherwise directly softwares cannot go and access, or they have limited access to certain registers like primary priority mask register and so. They don't have any access to system timers, nested vector interrupt controllers, or system control block. So they have no access. They cannot access. In unprivileged level, softwares cannot access these features. Softwares can access only all the features when it is in privileged level, or it also is restricted to use some of the features like FPU and MPU. Okay, peripherals and memories. So that means in privileged level, software can access almost all the instructions and have access to all resources. In unprivileged level, the software has limited access to most of the memory and peripheral related registers. This is one of the difference. That means privilege means access to all, unprivileged Software do not have access to all the features. Second, the modes, thread mode and handler mode. So when the system is running in a normal way, okay, when for example your computer, now my computer is running in a very normal way, it does not have any issues, right? So it is running, assume it is running in the thread mode. So when the system is running in a normal mode, it is running in thread mode. So assume my system is running in this way. Right now it does not have any issues, so my system is running in thread mode. But assume in between this, what I do, I remove the RAM from my computer. What will happen when the system is running? Okay, I deliberately manually remove the RAM from my system. What will happen? Anyone? Anyone? What will happen if I remove my RAM now? System is running very perfectly, smoothly. Everything is running smooth. But if I pull out the RAM from my system, what will happen?
System will stop working.
System will stop working. What does that mean? That means the system will crash, or the computer will get off. Computer
Get
will.
off.
So you mean to say the computer will shut down? Anyone
Right.
else? Anyone else? What will happen if I pull out my RAM or any other such important peripheral or hard disk in between the running of the computer? What will happen?
Sir, it will go to safe mode.
Safe mode. Okay. Second answer, it will go to safe mode. Anyone else?
Crash.
Crash. What does that mean? Crash. What will happen in crash? Okay. Nowadays it is very, what to say, not common, but in the past when we used to have Windows 98 or Windows XP, and whenever there were some conflicts in the driver and all, okay, so we used to get Windows. Have you seen this blue screen error?
Troubleshoot also.
Okay, have you seen? Okay, just let me show you something. Have you seen something like this,
Yes, sir.
Yes, sir.
or something
Yes,
like
sir.
this? So can you tell me why this kind of error, or why this kind of display appears in the computer, or when it appears? Like fatal exception has occurred, blah 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 blah. Press any key to terminate current application, control alt or delete to restart your application. So that means right now the Windows is working, right?
Yes, sir.
Still, when this message is displayed, the Windows is working. It is not that the Windows has it does not have any control on the system. So, or this kind of system, the PC ran into a problem, needs to restart. We are just collecting some informations. So, uh, have you seen this kind of messages or errors on your system? This is called exceptional error. So, when this kind of errors will occur, this kind of error generally occurs when my system gets into any exception. Exception means you can say an error, okay, or something has gone wrong with the smooth running of the system. Similarly, when the system is running smoothly, like this, right now the system is running smoothly, it is, we can call it thread mode. It is running in the thread mode. But whenever there is an interrupt or any exception means error mostly, or interrupts with very high priority, okay, those are called exceptions. And at that time the system gets into handler mode. It does not mean the computer or the microcontroller do not have any control over the system. No, it still has the control, but it has entered into an error based scenario. Okay, so you will have to restart it, reset it. Might be possible the things will get okay, otherwise you will have to check which error is occurring and how to fix that error. Okay, so that is called handler error. So when the system is running normally, it is thread mode. When the system is having any error in it, it is called handler mode or exception mode. Okay, so there is a difference between exceptions and interrupts. I will clear that also, remember. Okay, exceptions and interrupts, they are two different things. Okay, now coming to states. Thumb state, when the processor is running normal applications, most of the time it is in thumb state. Okay, again, just like thread mode, the state when the system is running normally, it is called thumb state. When the processor gets into debug mode, that means whenever you are going to debug the system, when you are trying to find the error or stop the error or check something, in that case we call it debug mode. Okay, for example, mm, let me show you a simple thing. Okay, because this feature is not available in your Arduino Uno board. Okay, of course, for that you will have to have a very expensive debugger for Arduino. Okay, otherwise you cannot see such activities taking place. Let me show you what I mean. Uh, okay, let me just show you something. Okay, it is taking time. Okay, before by that time I'll okay, here the system is ready. Okay. Okay, when you run this program in your Arduino, most of you might have used this kind of program or the basic blinking program in the Arduino board. Can you stop your program here or here? Can you stop your program on this line to check whether the LED is on or not?
No,
Can you
sir.
stop it after that? No. So
Uh,
that means no, because this microcontroller, the Atmega 328, okay, which is used in this microcontroller board, Arduino board, does not have the feature of debugging circuits. Okay, so to have that feature, you will have to purchase a very expensive, something like 11 or 12,000 rupees debugger separately. In that case, you can run the program and execute the program line by line. Stop it here, then after that you can spend some time for the delay, then again you can stop here so that you can check the program line by line. Okay, so debugging is that kind of facility which allows you to stop the or pause the regular running of any system, which is not available in the Arduino Uno board. For that you will have to buy a very expensive debugger setup. But in the Tiva C board that we are going to cover in this course, it has got inbuilt debugger also. What happened? Anyone having any doubt or something?
No, sir.
Okay, so now coming to the diagrams, the way to represent that thing. Whenever you start your Arduino, not Arduino, ARM Cortex M4 microcontroller, okay, or Tiva Seed Launchpad, it automatically goes into the thread mode, okay, with privileged level. So that means you have all the access to the registers and everything, and it is in thread mode, normal mode. In the beginning everything is normal. Then when your program start running, it might possible that you require some interrupt. When there is an interrupt, or we can say exception request, then what happens? It goes into the handler mode, because now you are going to handle exceptions. Okay, so from thread mode you can directly go to handle mode also. Oh, handler mode, in which what you do, you handles the exceptions or interrupts. Okay, still you are in privileged level. That means still you can access all the registers and resources of your microcontroller board. So right now you are in thumb state. That means still you are in running in a normal mode, but handling an interrupt. After that, from here you can come back to the thread mode. That means you, once you have completed the interrupt, you can come to the normal program. Or might be possible you may jump to thread mode with unprivileged level. That means you will not have the complete access to your registers and other resources. So first of all, this is the step. Thread mode, you can directly go to handler mode to handle the interrupts or exceptions. From here might be possible the system jumps to thread mode, that is normal return, okay, or it might be possible that you come to the thread mode with unprivileged level of support. That means you will not be able to access all the registers. Okay, from here again you can jump back to the handler mode and this loop can continue. So this is the basic mode in which the microprocessor or microcontroller is running. Apart from that, it is also possible that you can pause your system and enter into debug state. Okay, debug state means stop running the microcontroller, pause the operation, check whether your program is running in a correct way or not, and then from there you enter into debug state. Okay, you go to the debug state. That means it stops running the instructions, or you can halt the program at breakpoints. I will show you breakpoints and all. Okay, so it will halt, or it will, you can stop the programming for checking something. That is called debug state. Okay, from there you can come back to the normal mode and so on. This is all the journey of your microcontroller's program. Starts in a normal way, goes to handle the interrupts, may return to the normal mode, or may return to the normal mode with unprivileged levels, or in between that, if you want to stop the normal running of the program, you can enter into the debug mode and you can stop normal instructions or normal running of the instructions. You can call it breakpoints. Okay, I hope most of you might have used breakpoints in C programming. Have you used breakpoints in C programming or not?
Yes, sir.
Okay. Anyone who has not used breakpoints in C programming? Anyone? Okay, I will definitely go to those part when we will be covering the C programming, because right now we should cover these parts. Okay, please make note of these, and we will cover all these concepts while programming the microcontroller. We will cover each and every step. Okay. Now coming to the temporary registers which are available in the ARM Cortex M4. Remember the temporary registers in 8085? Anyone? What were the temporary registers in 8085? Please correlate and it will help you in future. How many temporary registers were there in 8085?
2, sir.
Temporary registers. Yeah, continue. Name them in 8085, the last course. A, first of all, accumulator. Then B, BC,
D, HL.
I should write it like this, BC.
Yes, sir.
Wait a second. So please try to correlate the things. It will make your life easier. BC, DE, HL, and then
WZ.
PC and
Stack pointer.
stack pointer. So these were the temporary registers which were there in the 8085. So it has got a very limited number of temporary registers. So you might have used the temporary registers to program 8085, and in some stages you might have thought that okay, there would have been more temporary registers who would have helped in my program, right? There are many instances there were many instances when even when I used to program, I used to think that okay, it has got only 6 temporary registers or 5 temporary registers. It would have been better if there were more number of temporary registers so that I can write more complex programs. Because what was the solution? Otherwise, you have to vacate the temporary registers. For that, you will have to dump these data to memory, right? And then you go and again change this value of temporary register. So temporary register is very important. The more the number of temporary registers, the more complex algorithms you can handle. So now coming to the temporary registers available in ARM Cortex M4, which are the temporary registers. So ARM Cortex M4 has got 16 temporary registers directly available, are from R0 to R15. Okay, so we can classify them into two different parts, low registers or high registers. Apart from that, you have stack pointers, which is it was there in 8085 also. Okay, can you tell me the size of these registers? Size of these registers?
32-bit.
32
Right.
bit.
Remember, these are all 32-bit registers. Okay, because ARM Cortex is 32-bit. So all the registers are 32-bit registers. Even the stack pointer, it is also 32-bit. Okay, then these are temporary registers, just like A, B, C, D, E, H, L, and all. Apart from that, you have link register. Okay, link register will hold. We will come to that also. It holds all the data related to the address or the returning address. It stores the returning address. Can you correlate what is returning address here? When you have to return to some address, for which kind of program you need this kind of returning address?
Call function.
Call functions, yeah, right? Call functions, and you used interrupts also, ISRs, right? Because before going to interrupt, you have to save the current address, or sorry, the next address, so that after completing the task you should come to the next address to continue your program. So returning address are stored in link registers. Okay, they help you to come to the next instruction. Okay, similarly, there is one important line which is program counter. Program counter was also there in the 8085. So remember, stack pointer, link register, program counter, these are all going to handle the memory, we can say. They will be mostly handling the memory related things, whereas these registers R0 to R12 will be handling the data related issues. Okay, so why it is called low register and high register, we will have to see that part also. Apart from that, it has got 5 special registers. Okay, these are all normal registers or temporary registers, and then we have special registers in ARM Cortex. We call them program status register. So can you tell me what will be the job of this particular register, program status register? Because here you can see the important word status. Whose status? Program's status, whether the program is running in which mode, which level, which kind of activity is being conducted by the program. All the details can be extracted from this PSR. Okay, then we have primary mask, fault mask, base primary mask. Do you remember masking, when we used to have masking? These were
Yes, ma'am.
Interrupt.
for interrupts, right? Interrupts related things. So which of the interrupts are exception? Okay, remember, exception means higher kind of priorities which are given to interrupts. I will show you that also. So exception or interrupts. So these 3 registers, okay, together are called exception mask registers, which will tell you the details about the interrupt related issues. Okay. Apart from that, one more register is there, which is called control register. So these are the 5 special registers. Apart from the normal registers R0 to R12, R13, 14, 15 are stack pointer, link register, and program counter. Okay, so let us look into these registers in a bit more detail. So R0 to R7 is low register, R8 to R12 is your high register, R13 is your stack pointer. It can be divided into 2 parts, main stack pointer and process stack pointer. We will check all these features. Okay, then R14 is your link register and R15 is your program counter. So program counter will point to that memory location where the program is currently being executed or the instruction is being executed. Now, what are the specialities of these low registers? Low registers that are R0 to R7 are accessible by instructions that specify general purpose register. General purpose means normal process and all. Okay, R0 to R7. Whereas R8 to R12, which are high registers, are accessible by 32-bit instructions. Okay, so R0 to R7 can be accessed by all instructions, be it 16-bit instruction or 32-bit instruction, but mostly R8 to R12 are accessible by 32-bit instructions only. So remember, I told you this ARM Cortex M4 can handle both 16-bit and 32-bit instructions. Okay, instructions are handled by this microcontroller. So R0 to R7 accessible by almost all the instructions, but R8 to R12 are accessible mostly by 32-bit instructions only. Okay, remember, R8 to R12 are not accessible by all 16-bit instruction. Maybe one or two or maybe few 16-bit instructions may access, but in general R8 to R12 are not accessible by 16-bit instructions. Okay, so that's why they are called high registers, because they are accessible by 16-bit. This one are both 16 and 32-bit instruction both. Okay, now coming to stack pointer, that is your R13, is used to point to the stack. Okay, where the stack is currently, where you are pointing to the stack. So it R13 points to the stack memory. Okay, remember, when I was talking about aligned and unaligned memory, remember I talked about aligned and unaligned memories. Aligned memories were those in which the system was aligned like this: 0, 4, 8, C. These were aligned for 32-bit data, right? There were half word also, which will be aligned at 0, 2, 4, 6, 8, and so on. So these are all 16-bit aligned, or we can say half word aligned. And byte aligned means almost every register, 1, 2, 3, 4, all the bits are 8-bit. So these are all word aligned. So that means 32-bit data, if they are aligned, they will always start from memory location which is ending at 0, 4, 8, and C. Half word, if they are aligned, they will start from memory address which have the ending address of 0, 2, 4, 6, 8, and 8-bit can go to any memory locations. Okay, unaligned means they can, of course, whether it is 32-bit, 16-bit, or 8-bit data, they can go to any address, right? So this is unaligned. But this is the concept of program counter, how the program counter is going to handle the memory. This is the issue with the program counter. But when it comes to stack pointer ignores all the memory locations which are not aligned. So it does not, stack pointer SP do not support unaligned memory access. It always supports aligned memory address. Okay, SP allows only aligned memory, and that too this memory, 32-bit aligned memory only. It does not support, SP do not support half word or byte alignment. Anyone having any doubt in this part? Look here, it is auto aligned to word, that means 4-byte boundary. It is not aligned to 16 or 8-bit. So stack pointer can never point to, or it will not point to memory allocations which are starting with 2, 4, 6 or 6 or something like that. These memories are not allowed in stack pointer. These are not allowed. 1, 2, 3, these are not allowed. Anyone having any doubt in this part? What is the constraint of stack pointer and what are the constraints of program counter, aligned and unaligned memory? If you have, you can ask again.
So can you give another example of an unaligned?
Unaligned, okay. Before going to that, okay, let us go to the slide where we were talking about aligned and unaligned memories. This, can you recall this slide?
Yes, sir.
Right. So 2000 0000, right? This is that address. Then this one is 01. This address is 02. This address is 03. What 03? 2000. Right? Got it?
Yes, sir.
Okay. So if it is okay, A is character, so that is 8-bit, 1 byte, right? So 1 byte data can go to anywhere. Does not have to check whether it is aligned or unaligned. It can be stored in any memory address. Whereas this is short. This is 16-bit. It will take two 8-bit, right? So it is taking two. This one. So if it is aligned, unaligned, so here it is starting from 01. So this is unaligned. That is why it is starting from 01. Whereas here, if you see, because it is aligned, it is starting from 02.
Okay, sir.
Right? So here it is starting from 04. So this is aligned memories, right? So program counter can point to these locations to access the data, but stack pointer to store the stack related data, it will never use these kind of arrangements. That means SP, stack pointer, do not support this kind of alignments. But here again, program counter is allowing you 02, 04, and so on. Okay, here also it can go 4, 5, 06, it can go to 06 for half word. It is allowed in case of program counter, but even these memories are not allowed in stack pointer. It will always start with 00, 04, 08, 0C only. Okay.
Okay.
So stack will
So,
never
sir, what is the advantage of aligned over unaligned?
aligned data can be accessed in a much faster way. So this helps you to increase the speed of the processing, right? But because here the accessing of data is more complex and storing the data is more complex also. Speed increases, okay, speed increases, but memory management is bad. Memory management is bad. Okay, I can just write memory bad. Memory means we are losing many spaces in the memory. Memory is wasted, or we can say wasted. Memory is wasted, but speed increases. Here, the speed is slow or it decreases. Okay, but memory is that is optimized. Memory is optimized, but speed is decreased. Okay, because remember, program counter is 32-bit. It should always be fast to go to 04, 08, 0C rather than clicking all the single bits also. Okay, so in general, when you start the microcontroller, it is always going to use aligned memory access. Otherwise, there are techniques in even in programming by which you can force the microcontroller to go to unaligned memory access also, but it will reduce the overall speed of the system. Okay, remember, this is trade-off between memory and speed. If you need all the memory, reduce the speed. If you don't want to, if you want high speed, always go for aligned memory access. Okay, so trade-off is speed versus memory. Okay, so this is all we covered. This we covered. Okay, so this is one very important point for stack pointers because they do not support. It is not clearing. Okay, they do not support unaligned memories. They always support 4-byte boundary. That means 048C. Okay. Okay. Now coming to link register, like I said, link register R14 is used to keep the return address so that whenever you are using any branch related instructions or linking related instructions, the program counter should know where to return back or where to come back. Even when you are handling exceptions or interrupts, okay, you need to know where to come back. So branch related instructions, interrupts or exceptions, they all need to know after completing the task where to come back, and that address is handled by link register. Okay, now program counter, we know program counter always points to the location where the program is or the instruction is being getting executed. So this is all the story about these registers, and when we will write the program we will be able to see all the things. Okay, now special registers, like I said, there are 5 special registers. Okay, so we call them together, we call them XPSR or program status register. Okay, PSR, we can say program status register. It is a combination of 3 registers. If you check here, okay, so see here, these 3 together are forming PSR, or we can call it program status. So these 3 will be talked together, or I will show you that. Okay, don't worry. So combination of APSR, EPSR and IPSR, exception, interrupt, application, all 3 registers joined together. Okay, so these 3 will be called exception mask register and so on. We will let us see what does that mean. Okay, this is a 32-bit register. This is also 32-bit register, and this is also 32-bit. So individually they are all 32-bit. Okay, please focus here. Individually all these register APSR 32-bit, this is also 32-bit, and this is also 32-bit. But if you see this, the way they have been arranged are a bit different. For example, these N, Z, C, V, Q, these are your flags. If you can recall from the 8085, there were flags in 8085 also, which used to tell us the status of the after the instruction or after any arithmetic instruction, what were the output, whether the output is having some zeros or it has got some carries or auxiliary carry or overflow. So similarly here we have a flag bits. So APSR holds the data related to flags. Apart from that, there is one more register GE, which is actually 1 or 0 depending on this comparison, greater than or equal to flag. Okay, so GE is greater than or equal to flag. So when you are doing this comparison between 2 variables, it will tell you about the GE. So APSR's 5-bit from 30 to 27. Okay, flags. Then these are all vacant, they are not used. You don't have to buy heart this, don't worry. Okay, but still know what are there inside this register. So GE means greater than or equal to, and then again these are not used, reserved. So they will be used in future, maybe for some other vendor or so for some other company. Now come to IPSR, right? Interrupt PSR. This is also 32-bit, but out of those 32-bit, you can see these are not used. These are all reserved, not used at all. From 31 to number 9. See, 31 to 9 they are not used in case of IPSR. Only 8 to 0 are used, which tells you the exception number. Okay, indicates whether exception has taken place or not. Okay, whether an exception has taken place or not, and whether the exception is being handled by the CPU or not. So this will tell you about the exceptions. So there are in total, if you check, 9 exception bits. Okay, exception bits. These are all theoretical part, but in the software we will see each and everything. So that's why I am showing you all these things, because when we will be running the software, you should know what is happening inside that. Okay, then comes EPSR, which is your execution PSR. Okay, in this you can see these bits are not used up to 31 to 27. ICT IT, 2 bits are used, which tells you interrupt continuation or if then. IT represents if then instruction status. Whenever you write some conditional function or something, okay, for exception, in that case if then bit is used, or interrupt continuation bit. We will explore them in more detail, don't worry. Okay, but just know the names. Okay, last, then 24th bit is your thumb state. It is always 1. Okay, for because it is running both 32-bit and 16-bit programs. So these are the bits for your these are the main functions of these 3 registers. But now if you combine these 3 together, see here, 31 to 27, here 31 to 27, if you take it from APSR, you will get these details. 2625, if you take the data from EPSR, it will be ICIIT. 24th bit again taken from EPSR. Then because here you can see these bits are not used, these are common here up this part, right? These are not used. So these are not used. So 20 to 23 are not used. Now coming to 19 to 16 GE, it is coming from APSR. 15 to 10 is coming from ICT, which is coming from EPSR. Ninth number bit you see is not used in any of these 3 registers. So ninth bit is also not used. Then you have exceptions number which are from 8 to 0, which is coming from IPSR. So if you combine these three, you can call them PSR together. Clear? Otherwise, actually they are 3 different registers, but they have been managed in such a way that none of these 3 registers bit are conflicting with each other's job. So you can, in total, you can make or combine them together to make them, or you can call them as PSR. Okay, PSR. Okay, there is no such separate PSR register. It is combination of these 3 registers.
Excuse me, sir.
Okay. Mm-hmm.
So, from
Yes.
23 to 20 to 23, why there is some space vacant
D. Where?
from 20 to 23?
20 to 23. In which? Here, this one.
In
Because they
BSR.
are not used. You see here, they are not used in here. They are not used in this part also. They are not
What is the
used in this.
purpose of leaving this space?
It is the company's job. We are not going to do that part, because these registers are going to tell you about some of the status of the program. Status means whether the program is running normally or not, whether there is an exception or not, whether you are comparing some bits or not, whether the number is greater than or equal to or smaller than that, whether the computer is running in thumb state or any other state. So this kind of detail, if you want to check, for example, you get some error, assume you are running a program and you got an error and the program is stopped, or the microcontroller is halted. Now you have to check because of which error my microcontroller is getting halted. So what you will do, you have the option to go to either of these three registers and check which bit is causing that particular error, right? So the company has designed the microcontroller or the registers in such way you can extract details from these register bits. Now I cannot tell you why the company has not kept this GE here, right? It needed four registers, so GE could have been here in these four registers, right? But why the company has not used it might be because of their design constraint or something like that. And why they have left these bits, I cannot tell you why they have not used it. Because of their design constraint maybe. But from the program's perspective, these are all the details which are provided to the programmer, so that in future when he is writing a program and he is getting a fault or any exception, or the computer or your microcontroller is getting hanged, in that case you can go and check these register to extract the details. But I cannot tell you why they have used these four registers, whereas there were four registers here also. They could have shifted GE here also. Yes, might be, but I don't know why they have not used it. Understood? So when you are asking this question 23 to 20 here, this range, you see they have not used these four registers either in APSR, IPS or EPSR. It is the company's prerogative. I cannot go and talk about them. Why you have left bit number 9 9 क्यों नहीं use किए? Is it a bad number, or it is having any bad omen or what? I cannot give that answer right now. They have not used, so they have not used. That's all. Clear? Hello,
Yes,
clear? Is it
yes,
clear?
sir.
Because I don't know why they have not used this part, because of some other constraint, or whenever you see reserved. Okay, remember reserved means in future microcontrollers they will use these kind of, or these memory locations for future applications or for future upgradation. They will use it. They are reserved. That means the company has an eye on in these registers. They will use it in future, or might be possible. Right now we are talking about TM4C, TM4C 123 GH6PM, this microcontroller. We are talking about this microcontroller, but it might be possible when you go to STM's microcontroller. This is from Texas Instrument, TI. If you go and open the details of STM microcontroller, might be possible you find that these three registers have a different sequence. So a programmer, before writing any code, should know the details of these registers, so that when he writes something, he should know how to debug the program in future. Don't worry, right now we are not going to use these registers, but I will show you all these registers, where they are and how can we access them in the software. Okay. Okay. So one more register is with the FPU, because floating point unit. Okay. Floating, because this is not available in all the microcontrollers. Very few, only latest microcontrollers have this FPU facility. M0 do not support FPU. Okay, M0, Cortex M0 do not support this kind of facility. I'm not sure about M3 also, but M4 supports floating point unit. So floating point unit, Cortex M4 floating point unit, again it has got this control register. This is control register, fifth last register, control register. Again it is 32 bit, between 0 to 31, and most important are these three bits: floating point, FPCA, SPSL, and TMPL. So these are thread mode privilege level. If it is 1, that means it is running on thread mode in privilege level. or if it is 0, it is unprivileged level. Similarly, FPSL select the stack pointer. Stack pointer has been selected or not, or to select the stack pointer, if it is 1, stack pointer is selected. Similarly, floating point is active or not. So if it is a microcontroller with floating point unit, this bit will be 1, and whenever you are using floating point related instructions or program, this bit will be 1. Otherwise, this bit is not available in all the other microcontrollers. So please keep an eye on control register whenever there is a floating point unit or not. Don't have to worry right now. Don't worry. Okay, just I'm giving you the architectural detail of the board. Okay. Okay. So what are the important things inside any ARM Cortex M4? So ARM Cortex M4 has got its own NVIC. It is called NVIC. Okay, this is very important unit. Nested vector interrupt control. So that means nested means a system or a loop which can be generated from a function which can be generated within a function, right? So nested function kind of thing. So it can handle nested interrupts. That means if there are multiple interrupts coming to your system, it still can handle multiple interrupts according to their priority. So therefore, we are calling it nested vectored. Vector, vectored means going to a particular address. Every interrupt has its own address for ISR. Okay, so nested vector interrupt controller, it has got its own unit for that. CPU, of course, the ALU and all those parts, central processing unit. But M4 has got one very important feature, what is called DSP, digital signal processing. So all my M4 Cortex are mainly designed for DSP related applications, DSP, digital signal processing related applications. So if you are interested in signal processing, okay, embedded system which are doing signal processing like your audio or video, small chunks of video and all, or image processing kind of stuff, you can use this kind of microcontroller M4. Okay, it has got its own DSP extension. Inbuilt unit is there for DSP, separate unit for DSP is there. Okay, it has got its own code interface, memory protection unit. Yeah, this unit is very important. Why? The memory is divided into separate units. I will show you that in the coming lecture. Memory, okay, let me briefly tell you here. We know that it is a 32-bit system. So you have 4 GB of memory. This 4 GB of memory is divided into separate sections. Okay, for example, code memory, RAM, exception memories and all. Okay, so whenever you are using code and assume the code enters into the RAM's memory, it will be memory corruption. Or whenever you are using stack related instructions and it gets into the RAM or something, it is again memory corruption. So to avoid such memory related issues, there is a separate memory protection unit available in your ARM Cortex M4. It is a total separate unit for protecting the memory only. Of course, apart from that, you have the SRAM and peripheral interfaces unit. And similarly, there is a very complex bus matrix. That means the bus inside the bus means the data bus, the address bus. Okay, inside the ARM Cortex M4 is a very complex bus architecture. Okay, and we will see that also. Then we have wake up at interrupt. That means whenever, for example, your system is in deep sleep. Okay, so when the system is in deep sleep, you can wake up the system by sending an interrupt. So there is particular unit which is always wake up at interrupt. That means it is even in deep sleep mode, it will be ready to accept an interrupt, and you can wake up the system through an external interrupt or timer based interrupt also. So you can wake up the system from deep sleep. So there is a separate unit for that. Wake up, interrupt, control interface. Like I said, there is a totally separate unit for floating point. Okay, floating point data are handled by this kind of microcontrollers. So floating point related totally separate unit for FPU is available. Apart from that, you have data watch point. That means where the data are getting stored and all. Flash patch and breakpoint handling facilities. And there are many other facilities like debugging the microcontroller and serial wire communication and all those stuff. That means you can even check what is the data being transmitted or received. Okay, so you can read all those stuff. So there are many such facilities available with the ARM Cortex M4. Okay, so these are the important blocks of any ARM Cortex M4. Now let us see and explore about the memory which I was talking to you. I told you it has got 32-bit memory or address line. Remember, 32-bit address line. Okay, so that means it can handle 4 GB of memory. Okay, so the first 0.5 GB, sorry, 500, yeah, 0.5 GB, 512 MB of memory is allowed for code, or we can call it code area, where you will keep your code out of 4 GB. Okay, and this is starting from 00000000 to 1FFF. So this is the 512 MB of memory for your handling of code. Similarly, there is 512 MB of memory starting from 2000 to 3FFF for the SRAM, for keeping the variables in your memory. Then there is a totally separate memory for all the peripherals. Peripherals, when we say peripherals, these peripherals can be ADC, DAC, timers, okay, and so on. Watchdog timers and all those stuff, whatever peripherals are there, all those peripherals have their own addresses. Okay, bitwise address also. So peripherals are provided 512 MB of memory space. So peripherals memory start from 4000. This is important, remember. Okay, 4000 to 5FFF. Okay, so all these memories, this memory range provides the detail of peripherals which are there inside your microcontroller. This is common for ARM architecture. Whether you take ARM Cortex M4 from TI or from STM or from any other company, this structure will be always same. Okay. Now, after that, you have external RAM memory, which is 1 GB of memory. Okay. Apart from that, you have external device memory, which is again 1 GB of memory. Then you have peripheral bus details of the addresses of the buses. Then you have peripheral bus, which is external, which is going to connect with the external devices and so. And then at last, there is a specific vendor specific region, in which vendor means, for example, TI is a vendor, Samsung is a vendor, okay, or STM is a vendor, Apple is a vendor. So different vendors will come to them and say, okay, I need this kind of extra facility in my microcontroller. For that, only this much of space is allowed between E0100000 to FFFF. So this is all 4 GB of memory. Okay. So vendor specific memory is very limited memory. Rest all the memory areas are always intact for all Cortex M4. Okay. So what are the important things that we have to look into this? This is a complete 4 GB memory. Okay. There is something called very important feature called bit banding. Okay. Bit banding. So some space of SRAM, okay, is kept apart for bit banding. Bit banding means the memory area here in case of SRAM starting from 2000 to 2010 that is 1 MB of space out of 512. Okay, keep an eye, out of 512, 1 MB of space is bit banded to 32 bit or 32 MB of memory. What does that mean? It starts from 2200 to 23FF to FFFF. Okay. Bit banding is one very important feature of ARM architecture. What bit banding means? Bit banding means each individual bit in this memory area, each bit in this memory area has got its own one 32-bit register in this area. So that's why 1 MB of memory, okay, from the bit band region has got 32-bit bit banding area in the alias. That means if there is one bit here, that one bit will be projected to a 32-bit register in this bit banded alias region. This is a complex concept. Okay, if you still have any doubt from this region, please do ask me. Okay, bit banding is very important. So remember, each individual bit in this region will have 32-bit register, separate 32-bit register here. So you can access this one bit even from here, even from this area. That means if you want to make this bit 0 or 1, okay, this bit, one bit can be either 0 or 1. And remember, there is no such instruction which can just change one bit of a register. Can you recall any instruction from 8085 which can change only one bit of any particular register? For example, you say register C. Okay, register C has got 8 bits, right? So C7, C6, C5, C4, C3, C2, C1, C0. Clear? If you have any doubt, please stop me. Okay. So register C has got, because this is an 8-bit register. Okay, this is 8-bit register. So this 8-bit register has got C0 to C7. Was there any instruction which can just make this bit 1 and rest of the bit zeros? Only change one of the bits. Was there any instruction which can take this kind of bit based instruction?
So and
No, for that you are using the whole register to add, right?
yes, sir.
So it is not a 1-bit instruction. It is an 8-bit instruction. It is going to change the whole register in total, right?
Yes, sir. Okay.
So here, using bit banding, you can individually change any particular bit of a memory or a particular bit also. But for that, because this is 32-bit, right? So what we can do, we have a 32-bit system. 32-bit system. What does that mean? 32-bit system, all the data will be 32-bit, right? And all the instructions will be 32-bit, right? 32-bit system means all the data will be 32-bit. Apart from that, all the instructions will be also 32-bit. So you can go and change this particular register, whole register, and that register will change only one bit in this region. This is called bit banded region. Banding means joining, right? Banding means joining or making, tying two things together. Banded, okay? So bit banded, each bit in this region, bit in this region is banded to a 32-bit register, individual 32-bit registers in this region. Therefore, if you see here, 1 MB of this region is mapped, or you can say mapped, is mapped to 32 MB of this region. So each bit from this region is mapped to 32-bit register here. We will see this detail in detail also, don't worry. Okay, but this is what bit banding is. So remember, bit banding, one region is this region, that is 2000, starts from 2000, and this is the region 22,000 onwards. Okay, one region is this one. So 1 MB, 32 MB. Now similarly, there is bit banding available for peripherals also. When we say peripherals, GPIO is a peripheral. Okay, your ADC is a peripheral, DAC is a peripheral, timer is a peripheral. So all these registers, GPIO will be 8-bit register, 32-bit register, ADC 32-bit, but you can individually access each bit of these peripherals, because these peripherals are again bit banded. From 1 MB of memory is bit banded to 32-bit memory in the bit banded region. So what is the range of that bit banding region? 40000000 to mapped to 42000000 onwards. So 1 MB of this space is mapped to 32-bit 32 MB of this region. 1 MB to 32 MB. One bit, each individual bit in this region is mapped to a 32-bit register in the bit banded region. So that means you can individually change the bits of even a GPIO. If suppose you want to make one bit of a GPIO 1 or 0, you can do that also, because it is bit banded. So this is called bit banded region. Okay, so what does that mean? Similarly, peripheral bus is also bit banded. Don't have to remember all these things. Okay, the addresses I am talking about. Bit banding is important, but okay. So these are all the bit banded regions where you can map one region of memory to another region of memory, provided, remember, one bit is mapped to a 32-bit. Okay, so using a 32-bit register, you can change even a single bit of the peripherals.
Sir,
Mhm.
so how are we going to select which bit we want to change?
I will show you that. Wait, I will show you that. Wait, where is that? Okay, no, stack bit banding. I have not shown bit banding. Wait, what does that mean, bit banding?
Sir, what would be the advantage of bit banding?
Advantage, simple. You don't have to, you can just individually select one bit. You don't have to change the whole register in total. You don't have to write a instruction for the whole register. Sometimes even you can write a program, or you can change only one bit of that particular register. You don't, without making any changes in the rest of the 32 bits. for not only for AND operation and all. We will come to that also. Don't worry. But just
Okay.
understand this concept, and this concept will be used to make or to make an LED on or off in future also. Okay. What is bit banding here? For example, uh, this address 2000, right? This address are there 2000, 2001, 2000. So these are bit banded regions from the SRAM, and they are mapped to a different memory address 22,000 or 22,000,000 onwards. So what does that mean? Each individual bit D0 is mapped to this whole memory. D1 is mapped to this memory, D3. So if I go to this address, if I go to this address and write 1, what will happen? It will show it will reflect on D1 only. If I write 1 here, okay, or make this register high, in that case, this register's output will be reflected on D1 only. Similarly, this register, if I make it high, it will be only reflecting in D3 only. Okay, so similarly, that means each bit is mapped to a complete one register of the other region. So this is one region, 1 MB region is mapped to 32 bit, 32 MB region. Both are the memory addresses, right? So you see the difference here. So you can access this whole register directly, one way. Okay, directly go to this address, write something. Or if you want to individually change these bits, individually any one of these bits, you can go to the next bit banded region and make change. And that will be reflected on an individual bit only. It will not be affected in any other bit. Okay. So that's why you see here, you are putting a lot of memory for one particular bit, but it will help you to further speed up the processes rather than writing whole register at once. Okay, so this will help you to individually change a single bit also. So these are all single bit region, single bits here, and it is mapped to a complete 32 bit register, right? So this is what we call bit banding. So this is how you remember this, because remember there is a memory starting from 0, 0, 0, 0, 0, 0, 0, 0 to F, 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 right? This was the memory, 4 GB memory. You have 4 GB here in the memory. So this 4 GB is memory. It is a huge memory. 4 GB is very, very huge memory for embedded systems anyway. In that, there is a memory somewhere here, 2000, 0, 0, 0, 0, and each of these registers individual bits are mapped to a memory 22000000. Okay, so this is called bit banding. So that means you can change the data either directly go into this memory, okay, or you can change individual bit by going to this region. We call it bit banded alias region. So if you make changes in this region, it will be only reflected on D0.
Excuse me, sir.
Mhm.
Sir, how like for a
Right?
one bit you can only put it one or zero,
Yeah. One bit you can put it 0 or 1. Here we will write 1.
but
Okay.
then how will it be reflected on the?
I will show you. I will wait. Don't worry. This will be shown in the examples also. But keep this concept in mind. That means you can change an individual bit by going to some other area of memory also. Understood? Just
Yes,
keep
sir.
keeping in mind. Later, when we will write a program to make an LED on or off, just an LED on or off, we will be writing a one particular memory region which will not be directly connected to that memory bit or the LED. It will be we may go to this region also, alias region, and we will make the LED on or off. Okay, just keep this thing in mind. Each individual bit is allotted a 32-bit register. This is called bit banding. Each bit has got its own address. Understood what I mean to say? That it is not that this is an address, right? D7, D6, D5, D4, these are all part of this address. Clear? This is clear. These are all the registers of 2000. Now, even the smallest bit has got its own address. Keep this in mind. It has got its own 32-bit address that is not available for all the memory regions. No, only few memory regions. One, especially in the SRAM, and secondly, it is available for peripherals. So these two memory regions have their own bit banded regions where each individual bit is mapped to a 32-bit address. How to use it? How to use this particular feature to make some outputs or change the behavior of the system or to make programs? We will explore that in future. But right now, because this is a new concept, just try to understand this thing. You don't have to write the whole 2000 to make a change in D0. You can come to this region, write something, and that will be reflected only in D0. This is what I want to tell you right now. Okay. Anyone having difficulty to understand bit banding? Okay. So I have 3 minutes before that. Okay. Just let me show you code blocks and show you some features of the code block. In 2 minutes, I will show you that. Then we will be, in the next class, we will be going more deeper into the ARM Cortex. Please make note of these things because everything that we talk right now will be used in programming. Okay, we will be exploring all these things while programming. Okay, C programming, let me just open a simple program and show you something. Because you might have used programs in the past also. Okay. Okay, so this program, most of you might be familiar with this kind of program. Okay, I have created one playlist for embedded C, so please do visit that also. So I believe most of you know this kind of programming. It is not that difficult right now, right? I'm going to show you something which is more important for an embedded programmer. How many of you know this part? Include stdio.h, stdlib.h, standard IO, standard library. We have included these things. I will cover this part also, don't worry. Then, this is how, what happened?
Screen is not visible.
Screen now? Is it visible now? No,
Sir, it was
Sir,
visible.
was visible
Maybe the
earlier.
not now.
Sir, now also it's visible.
No, my program, the code block is visible. Wait a second. Time is okay over. Code block is visible or not? No.
yes, sir, it's visible.
Yes,
Okay.
sir.
Yes,
Okay.
sir.
So the program is very simple. We have declared an integer type variable count. We defined some value into that count, and these are nothing but defining different variables, right? You all might have done this kind of programming. So now what I'm going to show you is I'm not going to run this program in one go. I'm going to stop this program from executing in one go. Okay. So what are the things that we can explore? If I use this button debug, press it here. Okay. So what are the things that we can see from this program? So let me show you. What happened? I think no. I will show you in the next class. Okay. Wait. Stop. Program is running on the other program. This disable both. Enable both. Okay. I'll close this program. Okay. Now I will run this program. still having some issues. Let me check. What happened? Okay, don't worry. Next class I will show you. This build warning. Okay, no issues. Go down. Okay. So see here, I have declared a value int. Okay. Now don't worry. We leave it. It's 2:31 now. I don't want to talk about all these things. I will show you in the next